So, welcome to problem solving session for Introduction to Group Theory. I am Siddhi Balu Ambure from IIT Gandhinagar, and today we will discuss problems from syllabus of week 9, that is problems related to class equations, applications of group actions, G-set and morphisms, and Burnside lemma. So, let us start with our first question. Yeah. Let G be a group of order 40. Then how many normal subgroups of order 7 does it have? Okay, and your options are 1, 2, 3, and 4. So this is the question. So we are asked that G is a group of order 14 and how many subgroups of order 7 does it have? And in the question itself, it is given that the option starts from 1. So by default, they are assuming that there exists a group of order 7. But now we have to check like how many of such subgroups, normal subgroups of order 7 this G has. But before going that, why we have this existence of group of order 7? Do we have any hold like there will always be group of order 7 which is normal in G14, and why is it so? So this is the theorem which we have, that let G be a group of, so this is for existence of normal subgroup of order 7. That why it is 7, and even if there were no options given here, and if you are giving exam and if this was NAT type question where you have to enter the answer, so how will you justify there exists at least one? I mean, no justification will be asked probably in the exam, but why will you start with the existence of at least one normal subgroup of order 7? So this is the theorem which gives us the existence of this group of order 7, normal subgroup of order 7. Okay, so and H be a subgroup of index P in G if P is the smallest prime number dividing order of G, then H is normal in G. So they are not saying that if P is the smallest prime dividing G and if I have a group of order that small p, I'm not talking about normality of that group. So this is, I have a subgroup such that its index is p and that p is the smallest. So here, so what is index of G? I hope you know. See, so if H is a subgroup, G is finite group, and H is a subgroup of G, then G index H is cardinality of G divided by cardinality of H. So this is the index. So this is the index of H in G. Okay. So this is what we have with us. So So here my G has order 14, and that is 2 into 7. And by Cauchy theorem, we have that for any P dividing order of G, there exists an element of order P in G, element X in G, such that order of X is P. This is what we have with us. So we can choose this X in G, and I will take the subgroup. We will take this H to be subgroup generated by that X. And then in that case, this G quotiented by, so we here G has order 14. So it is 2 into 7. So there exists one element of order 7 in G. And I will take now this H to be, suppose or X is in G such that order of X is 7. Then when I take this H, a cyclic subgroup generated by that X, then order of H is 7. And now index of this G with this H is 2, right? Because this is what? Index of H is this 14 divided by 7 here. Okay, so it is 2. And what here this theorem states that if P is the smallest prime number dividing order of G, then H is normal in G. So this 2 here, which is index of G with H, index of H in G. So by this here is smallest prime dividing the order of G. So therefore, by above theorem, H is normal in G. This H is normal in G. And when I say that H is normal in G, it means we have, that is, we have a subgroup H of G of order 7 such that it is a normal subgroup in G. I hope this is okay. So in general, if you have any group G using this theorem, in fact, if you have any group G of order PQ where by, if I assume that P less than Q, then there will always have a normal subgroup of order Q, because we can choose element X in G such that order of X is Q, and my H will be cyclic subgroup generated by that X. Then order of H will be Q. And then when I take this G, index of this H will be P, and that this P is now smallest prime dividing order of G. So now again therefore this H becomes a normal subgroup of G. And in fact, this is of order Q. So for any group G of order PQ, there where P and Q are distinct primes. So let me write here that P and Q are primes. P and Q are primes. So if I have G of order PQ, then we have a normal subgroup of order Q. So when I'm saying that normal subgroup of order Q, I am saying that I'm starting with the assumption that P is less than Q. Is this okay? So that's why we have the existence of normal subgroup of order 7 in this case. And now we have to calculate how many normal subgroups of order 7 does it have. So note that G has order 14, which is 2 into 7, and we can characterize the groups of order 14. Okay, so completely, because so there are only two groups of order 14 under isomorphism or with respect to isomorphism, and namely Z14 and D14. So D14 is D2 into 7. Okay, so this is dihedral group which we studied extensively last week. So this is dihedral group. And in both the cases, so once I have Z14, the only normal subgroup of order 7 is generated by 2. It is, so my H, which is generated by 2, this is the only normal subgroup in Z14. Okay, and in D7 also we have this cyclic group in D14, that is this D2 into 7 I'm here. So this, it is generated by this A and B such that A square is 2, sorry, A square is identity, B power 7 is identity, and this ABA is equal to B inverse, if you remember correctly. So this is what we have, and the only subgroup of order 7 here is this subgroup generated by B, and this will be the only normal subgroup. This is the only normal subgroup in this D14. Okay, so for group of order 14, we have only two possibilities. Either it will be isomorphic to D14. In that case, it will be subgroup generated by this 2. And again, in D14 case, it will be, so this is cyclic and abelian. Um, this is neither cyclic nor abelian. . So we have this two groups of order 14 here, and both of them have only one subgroup of order 7. So, and both of them are normal again using this theorem. So that's why there is only one possibility of normal subgroup of order 7. So this is the only correct option. Is this okay? So what we started with is we first prove that there exists some subgroup of order 7, and then we know that there are only two possible subgroups, not only two possible groups under isomorphism of order 14, and those are namely Z14 and D14. And in both the cases, we have only one subgroup which is of order 7 and is normal. So in Z14 anyway, any subgroup is normal. That's not a problem. And only two. So all other subgroups, I mean, generated by 4, 6, 8, and all under modulo 14. So when I write this is all the subgroups have only one normal subgroup in them of order 7. And that's what we wanted to calculate. How many normal subgroups of order 7 are there in these two groups, in group of order 14? I hope it's clear. If there is any doubt, please let me know. Is there any doubt here? If not, please. If not, then we will move to next question. No doubts, okay. So question 2 now. So let G be a non-commutative. So when we say non-commutative group, so it is equal. I mean, these are that exactly means that it is non-abelian group. Okay. So commutative is abelian. Okay. The terms are, when I'm writing this, it means this commutative means abelian. So it is non-abelian group. And non-abelian group of order PQ for some prime P. And now they're asking, like, what is the order of ZG? And first is these are the options. So G is a group, and just a second. Yeah, G is the group of order PQ, P is some prime. And now they are asking, like, what is the order of ZG? That's the question. So, any cases, what will be the order of ZG in this case? for that also we can use this theorem if you do not know. So at least you know that P will at least be order of ZG, right? Okay, I mean every subgroup of order P power n has center of order P at least. Okay, and so let me write this theorem for this question. So we are given that order of G is P power 3 here for some prime, and what is the order of ZG? What is the order of center of that group? So this is the theorem that let G be a group of order P power n where n is greater than equal to, sorry, P is greater than equal to 2. Then G is non-abelian if and only if the order of ZG is less than P power n minus 1. Okay, so they say that G is a group of order P power n, then G is a non-abelian if and only if the order of ZG is less than P power n minus 1. So here, given that G is non-abelian, okay, so in that, if G was given abelian, then the order of ZG will be this P cube. That's not a problem. But they have explicitly given that G is a non-commutative group and of order P cube. Then what will be the order of ZG? That's their question. And here they say that this statement say that G is a group of order P power n where P is greater than equal to 2. So P could be any prime. Then they say that G is non-abelian if and only if order of ZG is less than P power n minus 1. So order of ZG is less than P minus 1 means order of ZG uh, needs to be this. Okay, so and ZG is again subgroup of G, and since G is of order P power n, then this order of ZG would be P power n, P power k, where k is strictly less than n minus 1. Okay, so this strictly less than n minus 1 and the fact that, and what is the order of ZG? So in first note that in this is also one theorem which we can use here. If G is a group of order P power n, then for each there exists an element of order P power r. Okay, so this is a theorem which we can use, and using this for PQ, we will have some element of order P square in G. And if I take, if I take this G, this X in G such that order of X is P square, then This index will be P, which is the least possible. And we have a normal subgroup. I mean, we don't need this actually here. We are talking about ZG and not normal subgroup, but that's okay. But wait. Yeah, I mean, we need that actually to declare that. So every group of order P power n has center of order P at least. I hope you all know that. And using that, we can conclude that the options will be either P and P square. It will be among this. And using this theorem, we can say that G is a non-abelian group if and only order of ZG is less than P power n minus 1. So I want to say that order of ZG here will be P power 3 minus 1. It must be strictly less than P square. So the so since order of ZG must be strictly less than P square, it has to be this P. Okay, I hope this is clear. About the existence of, sorry, we still need to, I mean, check that. Or you can revise the notes. I think we have discussed this earlier that every group of order P power n has order of ZG greater than or equal to P. I don't know whether this statement is correct or not, but try to check that there are at least P elements in the center of G. Is this okay? I mean, we can also conclude this using class equation. We will see that in next few minutes. But since we have used this theorem that let G be a group of order P power n and P greater than equal to 0, I mean this statement, let us try to see the quick proof of this statement here. That because this theorem also uses class equation and other things about group action. So let us understand that. Let me just copy this theorem here. We will try to prove this. Prove that. So since order of G is P power n, then the center of G, that is ZG, is non-trivial. Okay, so as I've been saying again, that this since G is of order P power n, center of ZG will be non-trivial. Okay, so that's why the only possibility here was P. Therefore, order of ZG will be some p power k for some k greater than 1 and less than n. Okay, because we are given that G is a non-abelian subgroup. Okay, and we have to now find the order of ZG, what it will be. So it will be minimum between, so it could be p power k, where k is this, so that is k belongs to 2 to n minus 1. Okay, and now we will show that n minus 1 is not possible. Okay, so suppose G is non-abelian. So then there exists X in G such that X is not in ZG, right? Otherwise, the entire group will be abelian, because then every element will be inside ZG. Then the stabilizer Gx of X is a proper subgroup. Okay, so what is Gx? So Gx is all those G in G such that this. So this also means that this is G in G such that Gx is equal to Xg. So under this conjugacy action, we are considering this. We saw three actions last week, if you remember. One was left multiplication, which was xgx going to gx. Other was right multiplication, which was again xg going to xg inverse. And other was gx going to gx g inverse, if you remember correctly. This was our group. So this is a stabilizer of X, uh, and this is now proper subgroup. So, and we know, we also proved this last week, that stabilizers of any element are subgroups of, is a subgroup in G. So, no, like recall that. It was one of the questions in last week's tutorial, if you remember, that the stabilizer of an element in a group action, for given group action, is a subgroup of G. So therefore, this order of Gx will again divide order of G. So that is, order of Gx will divide p power n. So again, so therefore, this Gx will again have some order p power k, right? Where this k is strictly less than n. Is that okay? And since ZG, since X does not belongs to X, sorry, since X does not belongs to ZG, this imply that this Gx properly contains Zg, because since every element or H in Zg, let me write H in Zg, XH will be HX, right? Because it is in the center. And since X does not belong to Zg, it means that there are few more elements which commute with this G, right? So this imply that I hope you understand this, right? Because at least because whatever element are there in Zg, they definitely commute with this X here. Okay, so this always contains Zg. These are collection of all G's such that they commute with this X. And Zg is a set which commute with every other element of group. So I hope you understand this part here. And since X does not belong to Zg, this is proper containment, and therefore this I get this. This p power k is order of Zg from what we already have, is strictly less than this Gx, which will be some PR here, and this will be strictly less than G. Because this X is not in Zg, because I hope this, because since X does not belong to G, sorry, does not belong to Zg, because if X, because if this is happening, so this implies that X belongs to Zg, right? Because what is Gx? I know this is all this G in G such that Xg is equal to Gx. And if this is whole G, it means Gx is commuting with every element of this imply X commutes with every element of G. So this will imply that X belongs to Zg, right? But we started with X does not belongs to Zg. So therefore, this order of Zg is strictly less than p power r, this order of Gx. This is some p power r, which is strictly less than G. So if my G is of power p power n, then this will have at least possibility of p power n minus 1. And then this Zg by this will have order strictly less than p power n minus 1. That is, it will be of order p power n minus 2. Is this okay? So if this is some p power k, it has to be, this k needs to be less than equal to. Is this okay? Please let me know if this is okay. Let me go through the proof again. So we are starting with the G of order p power n, and we are talking about group that is non-abelian. So we are starting with some element X in G that is not in the center of group. So it does not commute with uh, every element in G. And then what is stabilizer gx of x? Under conjugacy action. Okay, so we are now making use of group action here in order to prove something which has nothing to do with group action. So this statement here does not need, I mean, this statement is independent of group actions. Okay, G is just group of order p power n. P is a prime and G is non-abelian, and we are saying that order of ZG is less than p power n minus 1. But here, if whatever information we have for group actions, we know that if I have a stabilizer of some element under group action, then it divides my, then it is a subgroup of my group G. And then it will definitely divide the order of my group G. And here we are working with conjugacy action. So under that action, this, so this is this is, let me write, this is left multiplication, this is right, and not right, this is right action, right group action, and this is conjugacy action. Okay, so under this action, we are looking at the stabilizers of element x, this x which we chose to be not in center of group, and then we are calculating this gx. And now note that it is what, it is collection of all the elements of group G such that gx is equal to xg. Okay, so here I just post multiplied by G and I got this equation. So these two sets are same. And the moment I have this gx such that it contains the elements which commute with x, it will definitely contain the center of group G, because in the center of group contains all the elements which commute with every other element of a group. Okay, and x is one of them, so center of a group will definitely be there. But since this is not a group which, since this is a group that will definitely have extra elements than center of a group, because uh, that's how we chose this x here. So it is now group subgroup of by group G, and it is also something is which properly contains ZG. So we get this, where is it? This equality, this relation here. Okay, please understand this part. Since since x is not in ZG, is properly this properly contains ZG. Okay, and since and ZG is also proper subgroup of G. Otherwise, so this is something which we have here. This relation p power k is less than p power r less than G, and that's it. Then G has p power n. Then possibility for this pk is something less than equal to n minus 2, because this gx which we are choosing, this x which we are choosing not in center, will give me some extra element in the stabilizer of this x. Is that okay? If there is anything confusing, please let me know. The only thing you need to understand is that this gx said here contains zg, which is trivial by the definition of gx, And also, this is properly contained in G. This is also you need to understand. That's how it is giving me that jump of p power n minus 1. And I mean, n minus 2, in fact. Okay. So this p power n here, p power n minus 1. This just says that it is less than equal to n by n minus 2. Okay. This need not be exactly equal to, but here, okay. So, and our question was pq. So the only possibility, so here I had p cube, which is contained in p square. So I had to choose some element which is not in zg, and its orbit will be of some size p square. I mean, this is just possibility, and this, so this could be anything between p power n minus 2 to p. Okay. And since the only possibility for cube case was p, we got this. And understand that any subgroup of order p power n has non-trivial center. L- Let me write this. Recall that. I think we used this multiple time before also, that every group of order p power n has a non-trivial center. That is, Zg is a non-trivial subgroup of G. Is this okay? So using these two facts here, we got that P will be center of G. So you can like remember this as a theorem. The question itself you can assume to be some statement that every group of order P cube has a center of order P. That's it. And please remember these statements which we are making here. These are the theorems which you can use. I mean, you can remember if you are planning on giving the exam for the course. Okay, any doubts here now? No doubt. Okay. So let us move to now next question. So let G be a group of order 81. Then which of the following is are correct? A, that G is a G simple. B, G is not simple. C, G has a non-trivial normal subgroup with more than 3 elements. And D, that all the above. So what is your guess? Like which one is trivial? I mean, when I say which one is trivial means, so note that order of G here is 81. So it is 3 power 4. Okay, so which one of the options is definitely false here? This is some p power k, right? So this is first is that G will not be simple. Okay, the reason being the moment I have some subgroup, not subgroup, the moment I have group of order p power k, we know that it has non-trivial center. And center is always a normal subgroup of given group G. Okay, so since, so I hope what group being simple means. Okay, if not, then group G is called simple if only normal subgroups in G are the identity and G itself. Okay, so it means it has no non-trivial normal subgroup in G. But the moment since G is of the order 3 power 4, that is p power k for prime p, G has a non-trivial center and therefore cardinality of G has non-trivial center, and since center is ZG is a normal subgroup of G, this imply that G is not simple. Okay, so the first option that G being simple is false, and we got that G is not a simple. Is this okay so far? We are heavily using that statement that every group of order p power k has a subgroup of has a non-trivial center. Okay, we are using that statement a lot. And now so this one is gone again. And now we have to check whether this is true, that G has a non-trivial normal subgroup with more than 3 elements. Can we uh, conclude this? Can we use any of the theorems which we saw earlier? Note that we saw these two results earlier. Not I mean, the first thing is for every group of order p power k, uh, we have an element of order p power r for every r strictly less than k. Okay, and secondly, we saw that if G is a group of order p power, no, G is a group and H is its subgroup, and if H has an index in G equal to P and P is the smallest prime of that kind, then that H becomes a normal subgroup of G. Okay, this theorem I'm talking about, the very first which we used today, this one. G is a group and H is a subgroup. Okay, so here since order of G or G is 3 power 4, there exists a group of order 3 power 3, 3 less than 4 in G and say H. Then for this H, index of G to H is 3 and this is like least prime dividing, in fact the only prime, the order of G. Therefore H is a normal subgroup. Okay, using theorem, if I call this star. So since it has a group of order 3 cube, that is 27 in this case, so G definitely has non-trivial normal subgroup with more than 3 elements. Okay, is this okay with you? Is Please let me know if there is any doubt. How we are concluding this statement, please. Uh, if there is any doubt, please let me know. Okay, I assume there are no doubt. If there are any doubt, please ask. Otherwise, I will move to this next question. Okay, so question 4, that let G be a second. let G be a group of order p power n for some prime number p acting on set S, and let S naught is equal to A in S such that GA is equal to A for all G in G. Then which of the following is true? First, that cardinality of S is congruent to S naught mod P square. P is cardinality of S is congruent to S naught mod P. And D is that S naught minus 1 mod P. Okay, so we are asked this question. And now how to deal, how to start with this. So we are asked something related to modulo P. And this GA is equal to A. This looks like uh, this so G is a group. So we have this right from the class. Let me write this in terms of class equation. If you remember, let me revise this again. Uh, so if G is a group and X is G set, G set means a set on which my group G is acting. So let if my XG is collection of all those X such that Gx is X for all G in G, this is just a notation, and this is what here S naught means. This is equivalent to S naught in our question. Okay, and this set, the set XG is also actually can be thought of as all those X in X such that this OX is a singleton X, right? Because what is this? The, this, what is orbit of X? It is all those X in, I mean, it is collection of all VGX, right? G in G. So every time my G is acting on this X, what are all the possible elements I get? This, if you remember, is called trajectory. It is called trajectory of X, or orbit of X. Orbit of X. So orbit of X. And what is it? It is whenever my G acts on X, what are all the elements from X I get? It is collection of all these elements. So this P G comma X is again in X. Okay, so when I say that Gx is X for all G in G, it means under this left, this is with respect to left action, left group action. Okay. Yes. So the orbit of this, we are collecting all the X such that orbit of that X is only singleton X. And now that I have this, and we know this statement, right? X is union of collection of all the orbits collection of all the disjoint orbits of X. And anyway, the orbit of two elements are either they either coincide or they are distinct. Okay, because see, we have, if Gx is equal to Y, then X is this G inverse Y. Okay, so either they coincide or they do not coincide at all. Please understand this. Understand that, note that. If you do not know this, the orbits of two elements in X are either equal or disjoint. Please understand this. And only then we are saying that Xg is collection of all the elements which are, I mean, who have singleton as their orbit. And so using this X becomes this collection of all these elements where elements with singleton orbit, and plus this is union of all this cardinality of orbits of X, such that is this X belong to F, this F is finite because X itself is finite. We are working on this. Is this okay? This is just collection of information which we have so far. And this is now is called as class equation. Is this okay? So this is the class equation which we have. And here this x is again, since we are talking about S, they are collecting elements of S such that this is what? This is O of A is singleton A, if you observe. And after this, we will do this theorem. So under this notation, we have this. I mean, this is the question they are asking, that if let n greater than equal to 1 and p be a prime number, if G is a group of order p power n acting on a finite set x, then x is congruent to this xg mod p. Okay, and this is exactly the statement which we have here, that G is a group of order p power n, and this is equivalent to that set xg. Okay, and this S is finite here. Then which of the following is correct? And from the statement which we wrote earlier, this is the correct answer. Okay, and we will prove that. And so since we are going to prove this anyway becomes false. That's not much of a problem. But here you can see that if P divides cardinality of S and cardinality of this S minus 1, we will see that how it will create a problem. As we proceed with the proof for this theorem, we will see that this is all cardinality of everything. Okay, so proof is that let G be a group and group of order p power n acting on a finite set x, and since orbit of x divides the order of G. Okay, so orbit of x also divides order of G, which we know. So it follows that this orbit of cardinality of this orbit of x will be p power nx, where nx is greater than equal to 1. Okay, because if this nx is 0, then then orbit of x will contain only one element, and then this x will belong to my set x power g. This will imply that x belongs to this x power g. So we are not talking about these elements. So we are collecting all those elements whose orbit is non-trivial. Okay, so then using class equations, I have this where p divides, let me use this, p divides order of G, that is this. Here for each OX, P divides OX, right? This. So since these are two equal, so under congruence, we can get this mod x, we can get rid of this one, and I will get this congruent to this mod p, right? Because this is p into something. Because this is what? This is collection of all the elements who has non-trivial orbit. So p divides everything here. So this becomes 0 under modulo p. So therefore this cardinality of x is congruent to x power g mod p. Since p divides this union, no, cardinality of this summation ox, x belongs to f, right? Cardinality of this will be what? This set is summation. This is summation. Is this okay? So class equation is just collection of, it's just writing x in terms of elements who are like, who are fixed under the group action, and elements who have some trajectory or non-trivial orbit under group action. So class equation is in short saying that the cardinality of x is union of these two kinds of orbits. And what this statement says is that this x power g is congruent to mod x. X power, this x power g means this set, cardinality of this set, which is collection of all those x which has singleton orbit, is actually congruent to cardinality of x modulo p. And we cannot conclude anything about p square because we do not know. I mean, p square, I mean, from the beginning itself, we do not know whether p square divides cardinality of x and so on. Okay, so this all the element statements are not holding here. Is this okay? Right. This, in fact, uh, direct application of class equation. Okay, so this was the question where we can directly apply class equation. And this question here, which we proved, the theorem which we proved here earlier, this was application of group actions. Because in order to prove this theorem, we actually went through the conjugacy action and so on. So is this okay? And if you, so let me also mention this here. So this was group class equation, and everything. But apart from this, if I take this, just what I can say, remark maybe, that if let G be a finite group, and this X be G. Okay, and G acts on X via, so now again this X is also G, via conjugate action. That is, this G cross X to X is such that G comma X going to Gx G inverse. Okay, and if you do not know who to invert, note that this X is, I mean, if you want to remember that this is this and not X G X inverse, the way to remember is that this X is any set on which my group is acting. Okay, the inverse makes sense only in group. It cannot be made sense in arbitrary X. Okay, for example, in the way Sn acts on the singleton 1 to n, which we saw in the exercise of last week, we can see that I mean, that's just way to remember this conjugate action, that G is the one which has inverse and not the X. Okay, so this is the conjugate action we have. Then this XG is what? From the definition, it is all those X in X such that Gx G inverse is my X again for all G in G, right? So it is what? It is all those X in X such that Gx is equal to Xg for all G in G. And what does this mean? This X is my G again, right? Here my X is G. So by definition, this is my center of G. Is there any doubt here? This is just basic definition, uh, which we are following here. And here order of X will be what? Sorry, orbit of X will be what? This is just collection of Gx G inverse such that G belongs to G. And this is conjugacy class of X, right? So here orbit is becoming conjugacy class of X, and my this set Xg, which we have here, is now becoming center of G. So using this, we can say that cardinality of this G is center of G plus cardinality of conjugacy class of each X. Is this clear? So the class equation which we have for any arbitrary group action G acting on X, not this is the class equation. We can write this explicitly for any given finite group G. Is this okay? I'm just simplifying the class equation for group and for a group under conjugacy action or conjugate action, whatever you want to call it. Okay, so please remember this. Uh, I have highlighted this useful for. Let me write this exam. Okay, so now this is the question. So I think this is question 5. Yeah. Question 5, that let G be this Gl2C and H be and AC non-zero, then every element of G is conjugate to some element of H. What does this mean? So H is given, G is Gl2C, that is all the invertible matrices in all the invertible 2 cross 2 matrices with entries from complex numbers. And H is this upper triangular matrices which are invertible because determinant is non-zero. Here the determinant, this AC, when I say, that is determinant of this, whatever this matrix, let us call this A. Determinant or determinant of this A0 is. Okay, this is the information we have. And now what they are saying, that every element in G is a conjugate to some element in H. So what does this mean? That is we need to check, and we have to check true or false. So what we need to check is that for all G in G, there exists H in H such that this G is equal to, sorry, yeah, this G is equal to HG H inverse, right? And this G inverse belongs to H actually. So we know that this actually comes from linear algebra, and it says that for every element in G, so for all A in Gl2C, there exists B in again this H we have, and some C in again G, this is my G, such that A is equal to CP C inverse. So there exists some invertible matrix and there exists some upper triangular matrix such that this A is CBC inverse. So using this, we can clearly say that there exists some matrix such that if I choose some element from G, there will be some matrix which will conjugate to this matrix H. So using this, we can clearly say that this A here, if I take this, then this is B and this belongs to my H. So therefore, every element in G lies in the conjugacy class of some element in H. Is this okay? If you want, you can explicitly give expression of this C, which comes from this. I mean, if you just have to solve some linear equations and you can arrive at this. Every element of G is conjugate to some element of H. Is this okay? Or, I mean, I hope you know this, right? This statement here. If you not, this comes from. If you know what eigenvalues and eigenvectors are, and if you know how to calculate eigenspaces, then you can easily get the expression of this C here. And we can see that the conjugacy action is G comma X going to G inverse, right? And this G we just need to calculate here in order to prove this existence. So we need to have hold of some element. When I multiply, it gives me some element from H. And that's how we can say that every element of G is conjugate to some element from H. And that's it. If there is any doubt, please let me know. Or is this clear? Okay, so if this is okay, if not, then we will move to next. This theorem, which I was, this is actually a result which you can understand, which I was you saying again and again. Let P be a prime and G be a group of order P power n for n greater than equal to 1. Then for every r less than equal to n, there exists a of subgroup H of G of order p power r. So here, which I was saying, there exists a subgroup. Okay, I again stated this theorem somewhere. I don't. There exists a subgroup of G of order PR. Okay, and that was giving me this existence of this. So we will try to prove this theorem here. So that this is the theorem which gives us uh, what we needed to say that there exists some normal subgroup of particular order in. So using this theorem, we can in fact say, so the direct application of this theorem using along with this, if I take this statement, if I call this theorem star here, okay, then for every group of order p power n has a normal subgroup of order p power n minus 1. Is this clear to understand? This statement which I just made here. So, because from this statement, what I have that for every r less than equal to 1, I have a subgroup H of order p power r. And the moment I have that, we can choose a subgroup of order p power n minus 1, say H. Then index of this H will be p power n divided by p power n minus 1. This will be p. And this p is smallest prime which divides order of G. And again, using that theorem star, then therefore using theorem star, we can conclude that this H is a normal subgroup of order p power n minus 1. Okay, we can't guarantee that there will be a subgroup of order p minus 2, p minus 3, and whatever that is. We cannot say anything about that. But using these two theorems, we can definitely conclude that for any group. So I'm highlighting this. You can also keep this in mind. So using these two statements, we can conclude that for any group of order p power n, there exists a normal subgroup of order p power n minus 1. Okay, so let us start proving this thing. This, if I call this result, proof of a result. And we are proving these results because these are the results which are, giving us application of class equations and application of group action in general. Okay, so we will prove this using the induction on n. Okay, so if n is equal to 1, then it's true, right? If n is 1, then if n is 1, then cardinality of G is P, and so cardinality of G is P, then the G is cyclic, P is prime, G is cyclic and has element of order P. Okay, so that P is P power 1, and for P power 0, I definitely have identity element in G. So that's not a, so order 1 element, identity element is order 1 element anyway. Okay, so the statement is true for n is equal to 1. And so since we are doing induction, assume the result is true up to a natural number. We are using strong induction. Okay, we are assuming the result is true for all the k's between 2 to m, and we will prove for m plus 1. Okay, so I hope you know the difference between induction and strong induction. In strong induction, we need to assume all the, so induction is I have base case true, I have nth stage true, and n plus 1 becomes true. Strong induction is I have nth case true, all n is equal to 2, n is equal to 3. The statement holds for all these n's between 1 to n, and then I prove using that it is true for n plus 1 stage. So mathematically it is weaker, but we call it strong induction. Okay, so we have this. So this is true. So let now G be a group. So when I say this, that is for all t this 2 less than equal to t less than equal to m, for G is equal to p power t, there exists a subgroup of, order p power k for all p less than equal to t. This is the statement. Sorry, for all k less than equal to t. This is what induction statement means. And so let G be a group of order p power n plus 1. So, so we know that G has non-trivial subgroup, right? This is anyway true for any group of order p n plus 1. So G has non-trivial center. That is ZG is non-trivial. Okay, and so let X be some element in ZG. So what I'm now saying, so ZG, so G is a group of order Pm plus 1. So it has non-trivial center. So I'm just choosing a element from center of a group, which is not equal to my identity element G. And let this K is equal to this cyclic subgroup generated by this G. Okay, then this order of X, this order of X will be this cardinality of K. This will be P power K for some K greater than equal to 1, right? This K needs to be greater than equal to 1 because I'm choosing some element in ZG. Forget about ZG. I'm choosing some non-identity element from a group of order P power K. So its order will be of the form P power T for some T. And that's what we are saying here. If I'm choosing any non-identity element of a group of order P power K, then order of that element is of the form P power N. So this X, anyway, I'm choosing from ZG, this statement here, this does not, this, I'm just writing this makes sense even if X does not belongs to ZG. Okay, I hope you understand this much. So I have this, so observe that now. This K is a subgroup of G. And in fact, it is a subgroup of ZG as well. Because anyway, X we are choosing from ZG. So it is subgroup of ZG. And so let R be less than equal to M plus 1. So let R be now less than equal to this small k by induction hypothesis. K has a subgroup H of ZG of order P power R. Okay, so we are choosing this R to be less than equal to M plus 1. And this K here, this small k here, this is small k here, and this is small k. So I'm choosing this R less than equal to M plus 1. And this R, if this R is less than equal to K, then by induction hypothesis, this K is less than my M plus 1. So there exists some element of order P power R for, because this now ZG, so again we are in the situation of this kind. So this is proper subgroup. So this ZG is of order p power r. So I'm getting subgroups of order p power r up to this k. Is this okay? So if I'm taking any r, so let me just push this down for better understanding. So if I'm taking some r less than equal to m plus 1, if that r is also less than equal to k, then this subgroup which I have here is of order p power m. Okay, so this k is less than equal to m. And if that is the case, using the strong induction, I will get subgroup of order p power r till k. Okay, using induction hypothesis. Okay, and so now if let r be strictly less greater than k, that in that case, then g quotiented by this k is a subgroup of order p power m plus 1 minus k, right? This is some p power k and this is p power m plus 1 and this is p power k. So this quotient will be subgroup of order p power m plus 1 minus k, and which is strictly less than p power m, right? Is this okay? Because k is at least 1. So this has to be of order strictly less than p power m. And since r is strictly less than, since r is less than equal to m plus 1 and r minus 1 is less than equal to m, then by induction hypothesis, we have a subgroup H1 of this G quotient K, which will have that order P power n, will be subgroup of order P power R. Okay, and hence if I take a pre-image, hence if we choose, if suppose if I have this P from G to G quotient K, which is of order P power this m plus 1 minus K, so it has subgroup H of any order between this and this number. And if I take pre-image of this, then this will be a subgroup of H. If we take this P inverse of this H1, if we take pre-image of this H1 under phi, then this H is a, and if I call this H, then this H is a group of order p power r here. Is this okay? So what we do is, for less than, we take the help of center of G. Whatever is the order of center of G, we will have element, all the subgroups of order p power r till that k. And for r greater than k, what we do is, this cardinality of this is p power k, and then this G becomes, this G quotient k is now a group of cardinality this, and this is strictly less than, this has cardinality strictly less than of cardinality less than equal to p power m. Okay, and the moment I have some group of order p power m, then for every r, I again have a group of order this H1, and when I take inverse image of H1, it will also contain this H in it, along with this extra R elements. So it becomes a subgroup of order p power r for r greater than equal to k. Is that okay? This H1 has, this order of this H1 is p power r minus k. And when I take pre-image of it, that k gets added because it was 0 under this quotient by k. I hope this is okay. For every, then it has a group of order p power r minus k for subgroup. Because the moment I get k, it becomes the whole group. Okay? For, and then its pre-image will be my required subgroup which we need. Is this okay? And also understand that why this holds is because pre-image under group homomorphism is again a subgroup of given G. So it again needs to divide order of G, and it always contains a kernel of G, which is in this case is of order p power k. And p power k plus the group of order this r minus k gets added, and we get element, a group of order r here. And this r is now strictly greater than k. Is this okay? So what we had is this groups till k, I have this zg, and the moment I go here, what I have is now this is my g, and this g quotiented by this k, which was generated by this x, This is now has order p power m plus 1 minus k. And for each such r, I have group of this order r minus k. Because now r minus k is less than m. So then this quotient h1, pre-image of this each h1, this r minus r, this will be r minus 1, r minus 2, up to this r minus k, and here I have element of order k and whatever. This becomes this h1 inverse p inverse of h1, which is of each order. h1, or let me call this hk. This is phi inverse of h1. Is this okay to understand? Please, if there is any doubt, please let me know. If not, then... So this is the only theorem which I wanted to do now. So therefore, this H becomes element of order H power. H becomes subgroup of order P power R. Is there any doubt? So see what we have. If there is no doubt, please let me know. Otherwise, I'll just give you a review. This group here, this G quotient K is of order P power M plus 1 minus K, right? And then this R I'm choosing greater than K. And I want to talk about group of order M. So if R is less than equal to M plus 1, this implies this R minus 1 less than M. And then by induction hypothesis, I will have subgroup of order this R minus 1 here, subgroup of order R minus 1 here in this GK. And when I take it back under this map in G, it will give me element of order, a group of order P power K. Okay, so this is R minus 1. Then for each K, by induction hypothesis, we will have a subgroup HK in G quotient K, this small a K. And this H now, this H prime, let me call it, will be this pi inverse HK of, let me just, H1. This H here of H1 is of order P power R. Because the quotient K which we got in its pre-image, it will get added. I hope you understand that. If not, try to do this with example and of order. p power k minus r. Okay, if flow cardinality of h becomes this p power r and this r was greater than k. So for both the cases, we got some candidate of order p power r. Is there any doubt? Please let me know. Otherwise, we can stop. If not, then I think we will stop. Thank you.